let me first say the title here is a little bit strange. What I want to tell you about is measuring the tunneling time and other problems in quantum archaeology. So as Paulo said in the introduction, I've been thinking about tunneling times for many years, but in fact, thinking about that problem as a grad student got me interested in a broader problem, and that's the perspective that I want to be taking now. I'll explain a little more what I mean by that, but I want to begin first by acknowledging all the people who really did the work I'm going to be telling you about now. The work on tunneling times on our Bose-Einstein condensate is on an apparatus that was originally pioneered by Anna Joffrey and Mirko Zirka, but the recent work, the recent publication, was led by Ramon Ramos, along with David Spearings and Isabel Racicot. Now that work's been continued by David, helped by Joseph, Nick, and Grace, as you see over here. And I'll also tell you at least a little bit about some of our more recent work, not yet published, that's being led by Josiah Sinclair, along with Daniela Angulo Mercio and Kyle Thompson. All of this work has benefited from the theory collaboration of my postdoc, Aaron Brodich, and of course, some kind funders listed on the bottom. And here's the perspective. What do I mean by quantum archaeology? We all know, thinking back to the Bohr-Einstein debates, that one can't look at present observations, like where on a screen a particle lands, and draw conclusions about what it did to get there. We can't ask which path it took on its way. On the other hand, classically, we do this all the time, and it's a cornerstone not only of our day-to-day thought, but also of many fields of science. And archaeology is one example. Cosmology is another example. You look at a bone or you look at the cosmic microwave background and you draw conclusions about what was there 65 million years earlier or 15 billion years earlier. Now, I think this conventional wisdom dividing the quantum world and the classical world is very misleading. And I would remember that as far as we know, there is no classical world. So when you look at that bone, you're looking at a quantum dinosaur bone. And when you conclude that the dinosaur used to walk in Missouri or wherever it was, you're making a conclusion about the past of a quantum system. So we do know from our everyday lives that you can draw conclusions about the past of a quantum system, even if you can't know exactly what the trajectory of a photon in a two-slit interferometer is. So the question that excites me is, in general, how much can we say about the history of quantum systems? When I make an observation now, how much do I learn about the past? And there's a very simple kind of straw man example of this that I always use to illustrate it. Some of you may have heard this before, either from me or elsewhere. But I think that you're familiar, as I was growing up in New York, with the way that people on the street like to try to cheat tourists out of their money and hide a dollar bill, or with inflation, it's probably a 20 by now, under one of three shells or one of three boxes, and mix them up and ask the hapless tourist to figure out where it's sitting now. And what I want to suggest to you is to consider a quantum version of this. Suppose I took a bill, and instead of putting it in one box or another, I put it in a superposition, a plus b over root 2, and asked you to figure out where that bill was sitting. Now, we all know you can't tell me with certainty. It could be an A, it could be an B, and I'm not going to cheat you that blatantly. I'm going to give you extra information. I'm going to promise you that when I later look for this bill, I find it. But I find it in a different superposition. I find it in b plus c over root 2. And my question to you is, given these two pieces of information, do you know more than you did just from the A plus B? Can you make predictions, for instance, about things like what is the probability that the particle was in B between my preparation and my finding the particle? I'm not going to try to do this interactively on Zoom. I've often done this interactively in meetings, and I'll tell you the basic result, which is the following. Physicists who haven't already thought about this specific problem are generally pretty silent, or say you're not allowed to ask that question, or just very simply say, well, I prepared it in A plus B over root 2, and therefore there's a 50% chance that it's in B, and making a measurement later may disturb it after the fact, but it can't fundamentally change that. Non-physicists, when I give this as a public lecture, there's always someone in the audience who immediately guesses what I think is the right answer. And the right answer is that it's in B with 100% certainty. And you can see this if you think classically, if you forget your quantum mechanics and you just think, well, he told me he was going to put it in either A or B, and he told me he found it in either B or C. It obviously couldn't be A, or he would never have found it in B or C. And it also can't be C because he put it in either A or B. So by process of elimination, it must be in B. And the interesting thing to me is physicists don't know whether or not it's fair to turn that plus sign into the word or, whether that reasoning actually works. And there is an experimentally well-defined sense in which it really does. And the answer is that it acts as though it were 100% in B. And I think this shows a gap in our intuition. I mean, we can do the full calculation. I can show you the answer, but we shouldn't need to work that hard, right? Our intuition should be good enough that we can do as well as the man in the street and say it was B. So this is just my big picture for why do we need to work harder to understand post-selected quantum systems. So here's the outline of my talk. I'm going to go into the particular problem I'm interested in, tunneling times, and that's got a century-old history, so I'll say a little bit about it. And then I'll tell you about our recent result, our experiment that probes how much time a particle spends in the allegedly forbidden region before being transmitted. And that's the post-selection. I'm interested in what happens if I see the particle got to the far side of the barrier. Do I learn something extra from that fact? Then I'll try to tell you with varying degrees of acceleration about some ongoing and future work, in particular what it would mean to ask where inside the barrier the particle spends its time. Also asking whether observation itself perturbs tunneling by looking for the particle in the barrier. Do I collapse it? What does that do? And then I'll at least advertise this completely different experiment. When a photon traverses an atom cloud instead of atoms traversing a barrier, how much time does it spend inside the atoms? And I think we've learned some really interesting things there, and there are more open questions. All right, so let us begin with the background of tunneling. You're all familiar with tunneling. There's an illustration. We're imagining a particle that has energy less than the height of the barrier. And of course, there's an exponential decay of the wave function inside the barrier, but then some probability to find it on the right-hand side. We all learn how to calculate this in our first quantum mechanics courses. But interestingly, most people have never heard the question and likely never asked themselves the question, how long does it take to get to the other side? Now, that's such an obvious question that you shouldn't imagine that no one asked that back in 1926 or 1932. They did. And if it's not taught in the textbooks, it's not because no one calculated the answer. I really think it's because the answer was so confusing that we were scared to bring it up in front of our students. We didn't want to raise something that we didn't really know how to explain. You could think about the problem semi-classically, right? Just to ask, what's the velocity of a particle as it propagates? And for that, I need to look at the kinetic energy. So I take the energy minus the potential. I'm left with the kinetic energy. I take the square root. It gives me a velocity. D over V is a time. And as I lower the energy towards the barrier, that kinetic energy goes to 0 and the time diverges. Of course, as you go further than that, you end up with E less than V naught. You have negative kinetic energy. And if you attempt that semi-classical approach, you get a negative kinetic energy and imaginary velocity. We, of course, don't know what an imaginary time would be. But we're not stuck with that. There's a very simple way that I think we've all learned for dealing with wave propagation. On the upper right here, you see a video that I stole from Wikipedia or something. We know how to do these time-dependent solutions. And you could just ask, if I know at which time the peak is moving towards the barrier, can I calculate where the peak of the transmitted particle is? And ask how long it took to get there relative to what it would have done under free propagation. And the way we know how to do that is the stationary phase approach. That's an approximation, but it turns out it's a good approximation here. It gives you what we're used to as the group velocity. But here's the problem. Remember what the wave functions look like. Up here in the barrier, we have a e to the minus kappa x plus b e to the plus kappa x. The stationary phase method asks how much phase has been accumulated by the time you get to the far side, and then takes a derivative of that with respect to the incident frequency. The thing is, the real exponential decay doesn't contribute any extra phase. So the phase over here on the right side becomes essentially independent of the thickness of the barrier. And that means so do its derivatives. So what you find is a time that becomes essentially independent of the thickness of the barrier, at least for thick enough barriers. And this is part of what confused people back in the 1930s, 1950s, 1960s. If the time delay is independent of d, the thickness, then for large enough, wide enough barriers, it can be less than d over c, and that can seem to violate relativity. The particle can seem to arrive sooner than it would have if it had been traveling faster than the speed of light. You might say, all right, Schrodinger equation is non-relativistic. I don't worry too much about these things. That's not the right resolution. People redid this problem using relativistic equations like the Dirac or Maxwell equations. The same thing occurs. Moreover, people did experiments, including me with Paul Kwiat and Ray Chow in my PhD thesis, a number of other groups as well, confirming that this really is what happens for the peak of the wave packet. McColl, who first wrote this down, and Hartman, who famously pointed out that saturation as a function of distance, were correct. And the peak can travel faster than the speed of light. Here's just some data from my thesis. I got really worried that people would just claim we had made a sign error somewhere, so we made sure to change the parameters so you could go from this left-hand region where the time is negative with respect to the vacuum propagation time to a region where it's positive. So at least if I made a sign error, one side or the other was going to be faster than light. We could conclusively show that we had seen that. Now I'm going to go through two asides. You should clearly be worrying. Does this mean energy is propagating faster than the speed of light? No, it does not. This occurs for thick barriers where the tunneling probability is very small. And I've illustrated that with some Gaussian tortoises or snails or something like that, attempting to tunnel through a barrier. And what you notice is that the particle that had to tunnel, wave packet 2 here, has a peak that crosses the finish line before that of wave packet 1, which was just propagating at c. But the height of this Gaussian is so much smaller that at every point in time, there is less probability to detect a particle if you put the barrier in the way than if you don't, or there's less energy reaching the finish line at any point in time with the barrier than without the barrier. So you don't need to postulate faster than light energy transmission. You just have to accept that for some reason, the energy that's being transmitted seems to come preferentially from the front of the wave packet rather than uniformly across the wave packet. So this was understood for a long time. When we were working on this, I was more concerned about the information problem. When the photon appears, have I captured information faster than light? But the answer again is no. We worked this out using Gaussian pulses that go on forever, which means that there's no point in time where you actually learn anything new from the signal. What I mean by that is if I give you some portion of a Gaussian, you can Taylor expand it and predict its future perfectly. That's true for any analytic pulse. We can even go deeper and think about how this arises in some tunneling geometries. Some of them amount to interference. I think this is the clearest picture for that. It turns out that when light, for instance, gets transmitted through a 99% reflective mirror, you're getting destructive interference in the forward direction. There are many, many different paths with multiple reflections, but each one is out of phase with the path before it. And when you add up all these wave packets, each one a little more delayed, the result is a Gaussian wave packet that looks just like the incident one, but is shifted forward in time. And that's a perfectly causal Green's function. It's simply a sum with alternating phases of different Gaussians with positive delays. And in this sense, the tunnel barrier, the mirror, is acting like a kind of analog computer. It's taking these different moments in time and predicting, if we have a low enough bandwidth pulse, if the pulse is analytic, what do we expect the future to look like? And as long as the pulse varies smoothly enough, that Taylor expansion works, and it looks as though you've advanced the pulse in time. If, however, you had a large bandwidth, a non-analytic pulse, this would all break down, and that's illustrated with this delta function at the bottom. If instead you sent in a delta function, the fastest thing that would get out would be the one that propagated with no reflections at the speed of light, and all these other reflections would just be delayed relative to that, and nothing would travel faster than light. I don't want to harp on this too long, but it's hard to bring up faster than light tunneling without having people worry about these two questions. So we need to begin with that.